Okay, so we are very pleased today to welcome our own postdoc, Tyler Hague, who is a experimental nuclear physicist and got his PhD extremely recently, in my opinion, in 2020 from Kent State University. He's one of 6 theses on the marathon experiment at Jefferson Lab, which stopped running 3 years ago.
2018.
Yeah, 4 years ago. He's going to talk with us about one of the most important pieces of physics coming out of that experiment, which is this, the distortion of quark behavior in nuclei, and specifically zooming into A=3 nuclei to see if the mystery follows the line of the mystery of everybody else, or if we have a double mystery on our hands. Anyway, Tyler, thank you for accepting our invitation.
Thank you for having me. Let me share my screen. And
By our invitation, I mean Shuji Lee's invitation. She got it first.
Okay. Hopefully there are no more typos in this. I caught one as you were introducing me. I fixed it just now. All right. I'm going to talk about the EMC effect. Subtitle, light nuclei are weird. So I'm going to give an overview of the EMC effect. I'm going to, where did it start? What's happened since? Where is it now? What did Marathon see? Where are we going? Kind of just a big overview of everything. So, right, table of contents, basically what I just said. Give intro, EMC effect, marathon, results. What are we doing? Where are we going? So intro, just back to basics, nucleon structure. So nucleons, protons and neutrons, 3 valence quarks, bound by gluons, and they have this, nebulous sea of quarks. So just the gluons flicker in and out of quark-antiquark pairs, and then they go back, and then they bind everything, and this constitutes the stuff in the nucleon. And so when I'm referring to nucleon structure, I'm talking about just properties of these constituent parts. What do we know about them? What are we learning about them? What is weird? What do we want to figure out? So things that we need to know, Bjorken X. Bjorken X is considered the, this is fraction of the parent nucleon momentum that is carried by a parton. So if you have like a proton, you have 1 unit of momentum. So if the parton in it carries all the momentum, it would have a Bjorken X of 1. We have 3 valence quarks, so naively we might expect that each one would carry 1/3 of the momentum, given by this kind of delta-ish function. But maybe there's some weird stuff going on. We've got C quarks; they can carry momentum too. So maybe it broadens a little bit. But nature's not that simple, unfortunately. So then we get into this momentum structure, and we see these things called PDFs. So parton distribution functions, just the probability of finding a parton with a given momentum fraction in essence. So we can see these are fits of parton distribution functions from data from H1, from Zeus. This is an old plot, but it's kind of illustrative of what we're trying to look at. So we see that these are definitely not peaked at 1/3.
Right. Okay. And you see this on this log plot.
Yeah, it kind of hides that being a log plot, but
Isn't
it's
that 0.5?
that would be around 0.2.
Oh, sorry.
So what's going on here?
Sorry,
No, you're good. You're good.
Sabotage your presentation.
So no, anytime you want to chime in, ask a question, whatever, feel free. I'm happy to pause and maybe I said something weird and maybe I need to explain it more. So just feel free to jump in anytime.
Are they going to jump in?
Yes.
But I mean, this is weighted by x. So even if it's sitting at 1/3, it doesn't mean that
How do we access these? These PDFs are not just something we can go in and measure directly. So instead we look at this F2 structure function. It's effectively the longitudinal momentum distribution of the partons, just all summed up and weighted by charge. So we see here it's the sum over all quark flavors of X times their charge squared times their PDF. And from looking at F2 structure functions of various nuclei, you can go in, fit that data, feed that into a model and get these PDFs out. So yeah, how do we access these though? We have a structure function, how do we get to it? The tool of the trade for this is Deep-Inelastic Scattering. In essence, Deep-Inelastic Scattering, lepton, in our case electron, comes in, exchanges the virtual photon with the nucleon, and scatters. In the case of Deep-Inelastic Scattering, the forward momentum transfer must be sufficiently large that the wavelength of this virtual photon is small enough to resolve the internal structure. It can see, I'm using air quotes here, the constituent quarks here and access these partons. And here we see, okay, we've got cross section for this type of scattering, and there's a whole lot of stuff here, but of note, it is proportional to F2. Now we have all of this other stuff that kinematics, and we can of course say, okay, well we did our experiment this way and put all that in and get F2 out, but then we also maybe want to look at the EMC effect, and so I'll get to how that fits in here. So EMC effect, all is not well in the nucleus. Nuclei, as I said, nuclei are a composite system of nucleons. Nucleons have quarks. Each nucleon has its F2 structure function, and each nucleus has its F2 structure function. Naively, it was assumed that the nuclear structure function is merely equal to the sum of its nucleon structure function parts. There are deviations at high X due to Fermi smearing, but that is understood, or air quotes. The European Muon Collaboration planned to use this assumption as a luminosity check in their experiment. They were studying, they were doing Deep-Inelastic Scattering on hydrogen, deuterium, and iron. So they said, okay, well, we want to get these structure functions out. Structure function ought to be the same for all nuclei minus Fermi smearing. So if we take the ratio of two of them, we should get unity, except for this kind of deviation at higher X.
So this figure is what they expected to see?
Yes, this is the expectation.
And so is it identically 1 until the Fermi smearing rise, or is there like a proportional dip that, I mean,
Yeah, so
kind of like,
there's a tiny slope there, but that's just smearing effects as far as the expectation went. This is my wonderful paint job of trying to just crop out the real data from here so that we have, whoa, that doesn't seem right.
Indeed.
So they took a ratio of iron to deuterium and saw this. That clearly is not unity. And so what's up with this slope? If it were a luminosity, so their intention was to check their luminosity. If it were a luminosity issue, then it would be just a straight up or down shift. So clearly this cannot be attributed to that. And so this unexplained structural difference in nuclei is now known as the EMC effect.
This is their original data?
Yes.
From the first crack at it?
Yeah, this is the first time this was seen. 1983. And so 40 years on, we're still trying to figure it out. So immediately after, SLAC said, well, we've got a linear collider. We can put we can put nuclear targets in there. We can map this out. Let's try and figure this out. So they said, okay, let's shoot electrons at these nuclei, really map out what this looks like. So they did a large A range. The strength of the EMC effect, quotes, is basically just defined now as the slope of this downturn. And you can see that the slope is changing with each nuclei. And so the EMC ratio is now defined as the per nucleon F2 structure function of any nucleus when divided by the deuterium. So if you take all your data at the same kinematics, you have the two Deep-Inelastic scattering cross sections. You divide one by the other. Everything cancels out except for F2. So by taking the cross section ratio, you effectively have the structure function ratio. And then now these nuclear cross sections are corrected for isoscalarity. So what's up with that? Deuteron's an isoscalar nucleus, Z equals N. For a fair comparison, we typically will correct the nuclei in the ratio to be isoscalar. That is, if there's an excess of neutrons, convert them to protons. If there's an excess of protons, convert them to neutrons. And to do that, you use this ratio of the neutron to proton structure function ratio. This has been extracted from deuterium over the proton, and if you just put in some Fermi smearing effects, you can get out the neutron over the proton structure functions because you've got neutron plus proton divided by proton, and you arrive at this slope, and you can then say, okay, well, make sure that you have Z equals N. You use that and convert neutrons to protons to neutrons, and then you take your ratio. One thing, I'm going to go back a slide real fast because I forgot to note one thing. Note this unity crossing in all of these around x of 0.3. That has led to this assumption that nuclear effects are minimized around x of 0.3. And so, okay, correct for isoscalarity, extracted from deuteron over proton. Further experiments are done. 2006, JLab EO3103 in Hall C used a 6 GeV electron beam, studied the EMC effect in a large range of nuclei, particular focus on light nuclei. In this case, we're defining that as A less than 12. And this was a precision test of our understandings of the EMC effect. So prior to this, the SLAC data all suggested that you have two really dominating features that drive your EMC effect. A, so just how big is your nucleus, and the density of the nucleus. So that was the test here. And we see our first weird light nuclei. Beryllium-9 is a clear outlier to establish trends when you look at the nuclear density versus the strength of the EMC effect. All other measurements look more or less linearly correlated, but beryllium-9 sits dramatically high above the trend.
So what means high and what means low on this plot? 0 means no effect and high means more suppression, or what does it mean? Or more slow, or steeper slope, or what?
Yeah, so the y-axis is the absolute value of the slope. So
Okay.
higher on the y-axis means that it is a steeper slope.
And beryllium-9 remind me, is that a nucleus where a neutron is floating around, or?
Yeah, 2 alphas.
Good question. So yeah, this has been used to suggest that the EMC effect may be sensitive to local structure because beryllium-9 is thought to be 2 alpha particles with a floating halo neutron. And so if you've got this cluster structure rather than just a dense ball in the center, perhaps that could be why it's this anomalously large effect, and it's really sensitive to your local structure.
Well, carbon is 3 alphas, but why is the alpha below them? That's the question.
So why is it like the alpha? They just made up a bunch of alphas. Shouldn't it,
That is a question that we don't have the answer to.
So
Well, two alphas next to each other are denser than just an alpha, or two alphas far away from each other.
Right.
Yeah.
So what goes into, more the tangent, but kind of just, what goes into the horizontal axis? It's, how do you, what do you, what's a model framework for calculating that number? Because you don't even have an error bar on that number. So.
Yeah, I think this was a Green's function Monte Carlo by Bob Waringa at Argonne National Lab, if I recall correctly.
So just, the size divided by mass? Just
Yeah.
super simple?
Yeah, using Green's functions and yeah.
So is this a pure experimental, or is there some kind of electron scattering data that go into it, kind of their radius and stuff?
Vertical axis is
I mean, the
data.
total.
Yeah, x-axis is
Pure calculation.
is calculation with data input.
Is there some kind of theory error bar on the horizontal axis?
There could be, there is not.
But wouldn't it be the same for every one of the nuclei? Who knows?
So it's the average density, right? So the structure effects show up, right?
Off the top of my head, I don't recall how big the uncertainty would be there. John, do you happen to recall that?
For the density, I mean, from the calculation itself, the uncertainty would be quite small. I think people consider these these are ab initio calculations that are generally considered to be pretty reliable, but it's hard to put a precise number on it.
Okay.
And they're not that different from what you get if you take electron scattering data to get the charge distribution and go from that, because that's what we do when we extend to heavier nuclei where we don't have these ab initio calculations, and they're qualitatively very similar.
So the plot would, so just to repeat what I think you just said, the plot wouldn't look all that much different if you just based it on electron scattering data.
No, it would not be significantly different.
Okay, good, that's basically the answer.
So, but the beryllium 9 is probably on the low side because of this neutron which sits out there in the outside, right? Which lowers the average density. Right? I mean,
Correct.
you have to twice the alpha density, it should be like helium-4, but now if this neutron rolling around, that should move it to the left.
Nevertheless, there's this huge nuclear effect.
Correct. Yeah, absolutely.
Sorry, just to kind of
Yeah.
test my understanding here. So the Fermi smearing is basically assumed, like that's like a single one of the nucleons that you're correcting for the effect of that, but then when you say you go to different nuclei, like why isn't the Fermi smearing correcting? Sorry, maybe that didn't make any sense.
No,
I mean, like what's the Fermi smearing correction, versus this that we're seeing?
Yeah. Yeah, so I understand your question. I'm thinking of if I know the answer off the top of my head.
Maybe you fit the slope outside of where the Fermi effect is expected to be large.
Oh, got it. Yeah. So the slope is fit from x of 0.3 to 0.7. Just if you want to, that's where the downturn is localized-ish. And if you go beyond x of 0.7, yeah, that's when Fermi smearing starts really like coming into play. And so we don't fit that for the slope. We just say, okay, well, below 0.35, 0.3, you've got anti-shadowing and shadowing, so we don't want that mucking up things. So let's chop that off. Let's chop off Fermi smearing and really just get this kind of linear region that shows up as linear in every nuclei that we've looked at so far.
So Fermi motion affects mostly toward a larger axe, right?
Yes.
That's what it folded into nuclear wave functions, for example.
Really? What did you say? Sorry.
Oh, it's just that the nucleons is in motion, right? So you're
Yeah.
measuring this thing, in general, folding that motion will be like factorizations and so on, if x over y times function of y.
Is it correct to say, like, my intuition for this is that if you have a quark sitting out at x equals 1, it has all the momentum of the nucleon. So if you put it in an environment where it has some Fermi motion, it's going to behave very strangely. It's going to have a lot of motion that it wouldn't have sitting by itself.
One is more extreme. He's thinking that every given particle in a nucleon, but the nucleon itself is moving, right? So it's a folding up to the product. It was in terms of probability, it's a product problem, not the sum. The other one's the sum. This is product. And consider pi. You have a pion cloud model. Cover some relations. Go to pion as long as u bar minus g bar difference. Consider the solving process where the pion, there's a pion inside there. The pion has a moment you could couple the nucleons. So you have the quark inside the pion and pions in the process. Because that's the same formula. Just like evolution, when you go to evolution from one scale to another scale, you have this folding of probabilities, and that basically people do, I think, is the smearing is quark and folded with the quark. The fact the quark is also the nucleons also.
But it is true that the quark at x equals 1, if you give it Fermi motion, give the nucleon Fermi motion, and the quark has all of that motion, it's going to behave very differently in the nucleus than it is in a bare
If
nucleon.
nucleon is x1, does that mean that
No, the quark, yeah.
all the quarks are 1, and then there's no more, you have a binding energy, right? You have a binding which is smaller.
You're doing more sophisticated stuff because you know what you're doing. I'm doing something very simple. I'm saying x0 k of 1 says the quark that you struck carried all of the momentum of that
Of the
nucleon.
nucleon.
If you put that nucleon in an environment where it has some Fermi motion, that quark behavior, the F2 is going to
They
go
have
like
extra motion. Yeah, okay, yeah. Good.
Alright, so Beryllium 9, weird, breaks established trends. So now that was 2006, now we go to Marathon 2018. So this Marathon had a few goals here. So we're mapping the A equals 3 EMC effect. So Marathon was unique in that we had a tritium target, which is not terribly common. So in this case, there's a few things difficult there. Tritium's not stable, it decays. Tritium is radioactive, so it's not terribly safe for the people that need to work around it, install it, all that. And so that doesn't come too terribly often. But so Marathon aimed to look at the A equals 3 EMC effect. So before we get to what Marathon did, let's revisit F2N over F2P. So before I said, previous data assumed Fermi motion and used a smearing model to extract from deuterium over proton. That extraction has been revisited since then, and found that there's a lot more than just Fermi motion going on in the deuteron. If you include more sophisticated effects, you go to a more sophisticated model, you've got a whole lot of different predictions on what this extraction actually would look like, depending on what you understand about the deuteron. If your understanding is correct, you can say, okay, well, maybe it keeps falling, maybe it levels off, maybe it shoots way back up. This is an open question because the answer requires understanding the deuteron structure. And so F2N over F2P, that goes into your isoscalar corrections. So if you've got a big uncertainty there, then suddenly you've got a big uncertainty on your EMC extraction. and you also just simply say that you don't know the neutron structure. You can get protons F2 pretty straightforwardly because you can have a proton target. You don't have a neutron target, no free neutrons. So we can't easily extract that. We have to get it from other nuclei, and these are significant limiting factors for understanding the EMC effect. So yeah, we need to figure that out. So I put here, what if we could get rid of nuclear effects? And for legal reasons, that's extreme hyperbole. Okay, extractions of F2N over F2P from D over P are limited by our understanding of the nuclear effects of the deuteron. Nuclei that are sufficiently similar, though, may have comparable nuclear effects. So deuteron and proton, you've got proton plus neutron divided by proton. That's two very different things. If you look at similar structured nuclei, maybe their nuclear effects could cancel. You take their ratio, and then you're really only sensitive to the ratio of nuclear effects, which if your nuclei are sufficiently similar, perhaps that can be very small, and you can minimize your model dependence of the extraction.
Sorry, what do you mean by sufficiently similar?
In this case, A equals 3, so you've got just three nucleons. So you're comparing, in this case, helium-3. So you've got 2 protons and a neutron versus tritium, which is 1 proton and 2 neutrons. So you have a difference, but you're just looking at a small 3-nucleon system. And so hand-wavy nuclear effects might be similar because you're looking at similarly sized things. So as we looked before, we said things seem to scale with A. Maybe that's not perfect, especially when you look at like beryllium-9, but it is approximately true, at least for what we've looked at so far, with some exceptions. So we can kind of say, oh, well, let's take a look at this and see what we can learn. So yeah, why do this new experiment? A equals 3, smallest system with mirror nuclei. So we have 2 nuclei with the same number of nucleons. And so we can also look at the difference between proton and neutron modification, hand wavy. That's you have in helium-3, you have N over Z is 2, or not 2, 1/2, whereas in tritium, you have N over Z is 2. So you have this striking difference. And then, okay, so then you can also say, if we assume that the difference in nuclear effects is small, that is, when you take the ratio, it largely goes to unity, then you can better assess the free nucleon structure function ratio F2N over F2P. Free neutron structure is poorly constrained by prior data, as we saw in a couple slides ago. We don't know these nuclear effects very well, and so when you look at F2N over F2P, as you go to higher and higher X, that possible values based on different assumptions is just wildly unconstrained.
So is it kind of expected that the Coulomb repulsion between the 2 protons basically has no effect on this experiment?
So that is kind of just built into nuclear effects, and it's expected to be small-ish, sure, but yeah, that's just kind of baked into the nuclear effects. And so if we can better constrain this rate F2N over F2P ratio as X goes to 1, then you can also kind of get at the better discerning between different models of how the internal structure works. Each each way you look at it can make different predictions of this ratio as x goes to 1. You can go SU6 is 2/3, diquark or quark models both give 1/4, perturbative QCD and quark counting give 3/7. These are different numbers, so if we can kind of tell where it's heading, then we can start saying, okay, well, back to the drawing board, let's figure out what does the data support and what does it not support.
Tyler?
Yes.
I'm kind of hung up on what Henry just said. The strength of the strong force versus the strength of the electromagnetic force, is it like a 5%? Like it's much, much smaller, we know that. And I know that we always neglect that we have isospin symmetry. I forgot the
Offhand, I don't have a number in mind.
I'll look it up.
Yeah.
John has a question. John?
Yeah, I was just going to say for that. So for the Coulomb effects for heavier nuclei, we sometimes correct for those. And these sorts of kinematics, you're typically talking most of the time it would be 5% or less, except for very heavy nuclei. It's particularly small for these because not only is it low charge, but they're also large radius. And in fact, there's an argument to be made that you should not correct for it for tritium, but that's a more technical philosophical argument.
Very good.
So before we get to what Marathon did to do these things, let's do a quick tour of the experiment. Marathon happened. The Marathon experiment ran at JLab, which is in Newport News, Virginia, all the way on the other end of the country. Just was there a few days ago. CBAF is the accelerator. It stands for Continuous Electron Beam Accelerator Facility. It's this racetrack accelerator, and I'm going to move my mouse to just kind of highlight where it is. You have these two, basically you have two linacs that are then connected by this this bend, and you can go around the racetrack up to 5 times to increase your beam energy. And so for each trip all the way around, you get 2.2 GeV because you go through 2 linacs. And I put the approximately because it's always less than that. I believe, had 1.06 GeV per linac pass, and giving 5-pass beam of 10.6 GeV. And so electrons go around there, and you go off here, and you have these 3 halls right here showed by these mounds of Earth built up. So you have Hall A, Hall B, Hall C. We ran in Hall A right here. Not shown is Hall D, which was not built when this picture was taken, but they cleared out some trees and put a hall back here. So like I said, we had a tritium target. That's new. That's not often done. So that was fun. We had our 4 cryo targets. We had tritium, deuterium, hydrogen, and helium-3. We had specially designed aluminum cell to accommodate this. And these were specially designed in that often cryo targets at JLab will be circulated so that you maintain more or less constant target temperature throughout the length of your extended target cell. So when an electron passes through it, it will deposit energy and that heats up your target. And if your target changes temperature, then you've changed your density. And so you will circulate that in order to, as the beam heats it up, you then recool it and pump it back in. And so you've got this system that circulates and keeps you at a pretty constant temperature. Tritium, we didn't want to do that. Tritium, so we had a whole lot of safety procedures surrounding using that target. We did not want to circulate it because the more you move it around, the more different places you get it, the more failure points you have, and you risk leaking your tritium. And we don't want people exposed to that because it's radioactive. Instead, we just had a extended target cell, no circulation. We did passive cooling with this giant copper block that is put at the on the aluminum block of the cryo targets. We had a current limit because we didn't want to risk electrons punching a hole through the aluminum and leaking tritium. A whole lot of safety procedures, but we did it. We understood it. It was awesome.
What's the size here of the copper
Oh, yeah.
cooling thing?
We rotate. So these cells are 25 centimeters long. So I would say that's probably around 50 centimeters, maybe, if I kind of rotate and then it's further away and kind of guesstimate from there. It's not huge. And so, okay, beam comes in from that accelerator, bends into Hall A, shoots through our targets, electron scatters off of your target and goes off at some angle. We've got in Hall A 2 high resolution spectrometers, HRSs for short, and this is the left HRS on screen. You can see there's no people in this photo for scale, but this ladder is approximately a person tall. So call that 2 meters, it's really big. So these use a magnet setup, 2 quads followed by a dipole followed by another quad magnet, just to bend bend electrons up to your detector stack and reject everything else. We want to keep electrons, we don't want to keep anything else. And so in that detector stack up here in this big area, this enclosure, you can see these doors are open because someone is working in there, possibly me. In there you've got tracking, PID, calorimetry, so drift chambers, scintillator planes, 2 calorimeters to detect the full energy of electrons, Cherenkov for particle identification, pion rejection basically. And that's our detector setup. So once we've done this,
Yeah, nice, good. So your targets, they're like, atoms, right? So there are also electrons there. Like,
yes.
how is there some way that you can like completely cancel like the effect of like molar scattering?
Ish. I mean, so these spectrometers only accept a very small momentum resolution.
I see.
And so dominantly when you're doing molar scattering, I mean you're doing
The kinematics.
yeah, kinematically the momentum of your scattered electron is not going to be the same as a deep and elastically scattered electron because just the mass of what you scattered off of is so vastly different.
Right.
So
I see.
nominally that can happen, but kinematically it's extremely suppressed at the momentums we accept.
I see. So yeah, so it's not like you're kind of taking everything and measuring. Yeah, it's like you have some tiny window that you're
Right.
not sensitive to. Okay.
Right. So yeah, we set the momentum. I don't recall off the top of my head what the number was. I want to say ballpark of like 9 GeV, and then we just rotate it. So you can get at different Bjorken X by having the same momentum accepted at different angles. So nucleons are modified. How are we getting these free nucleon structure functions out of tritium and helium-3? We assume the modification will be similar for each target. We can use a model to remove the differences in this curly, funky little R thing. We're calling that the super ratio. R is a super ratio of EMC type ratio. So normally your EMC ratio is your nuclear structure function divided by your deuteron structure function. Instead, you can take a model, say, make a prediction for your F2 nuclear structure function, and then divide it by the sum of the nucleon structure functions of that nuclei. And that is effectively quantizing what your model predicts the difference between the nuclear structure function and what we 40 years ago assumed the nuclear structure function would be. And from there you can make your prediction.
That's a question. Of course, the R, of course, presuming you want to use R to define this F2 neutron proton ratio, right?
Yes.
The R itself it depends on the F2.
Yes.
Right?
Yes.
So do you do it iteratively, or how do you?
So we did not iterate here. In principle, you could.
So what is the input for the say neutron F2 in R?
So that the input is so you've got all of your previous scattering data, and you build your model around that. And so we have so I showed the F2N over F2P predictions before, where okay, first there's the line, then there's the divergence at higher X. So each model has their different, like, here's what we assume the nuclear effects in the deuteron are, and they extract it from that. And
Right.
F2P is well known, so if they say, well, these are our expected nuclear effects, we get that, and then they can each make their prediction for the super ratio. You're absolutely right that an iterative procedure could be useful here. That was not done in this case, but it was discussed.
So the different model input for the F2N, you have a different results, right?
Right.
Or, oh, they're similar somehow. Would that be in the end similar?
We'll get there.
That is, that would be true.
Yeah, that is a good question, and the answer is yes. It is different, and we'll see that a bit in after the results are flashed up here.
But Tyler, there's no model dependence in the super ratio. This is just a definition, right? These F2s, no models yet, except maybe isospin symmetry. Or am I wrong?
So there's no models in the sense of that is it's a defined quantity, but the value of the super ratio, we just said, let's use a model that gives us this and then extract from there. So we didn't measure the super ratio. We just said, okay, well, we measured helium-3 over tritium, and then we took a model of the super ratio and used that to extract F2N over F2P.
You took a model of R,
Yes.
clearly R.
And then you input that into this equation, so this ratio, helium-3 over tritium, is data. This super ratio is model. And so you have this F2N over F2P extracted, which, as we saw before from the deuteron over proton, is a model-dependent quantity. And it absolutely is here too. The question is, can we reduce the model dependence from what deuteron over proton gives you? So the super ratio model. Official marathon analysis.
Yeah, can you go back to last? This is still you have to assume some kind of nuclear dependence of the structure function in order to extract the ratio of neutron to proton, F2, right?
So so we assume that there is some sort of nuclear effects going on, and that is baked into the super ratio, and that's why we get it from a model.
Yeah, so there is still some kind of model dependence on the, as I said, on
Absolutely.
the nuclear. Yeah. So I don't think there's any way you can do this model independently.
That is correct.
Yeah.
We
Have you thought about using different isotope? I mean, like what they have done at Rig for different isobar, especially when the nuclear number is. I would imagine that the nuclear effect are similar.
But that's what we have here. It's just two isobars, right? I mean, it's in the trivial.
Yeah. Well, I'm saying that when the nuclear number is large, so you would expect this the other, the difference due to different isotopes are small compared to the normal nuclear. That what I'm saying that when a nuclear number is large, the isospin dependence of the nuclear effect probably is small.
okay.
Maybe John has something to say
Yeah, I
about that.
think John wants to say something here.
Yeah, so you could use two nuclei that are very heavy and just one has an extra neutron. And if you just did that subtraction, you would basically get a smeared neutron with not much model dependence for the nuclear effects. But you'd get a smeared nucleon in a heavy nucleus with a lot of smearing. The idea here is you're getting a smeared nucleus in a light, a smeared nucleon in a light nucleus that's well understood and has smaller corrections. So this, you could do it that way, but then you look at a different model dependence. This is kind of
but in this way, the isospin dependent of this ratio for the small nuclei could be quite large compared to the other effect.
Well, you can consider calcium-41, scanning-41, and all these isotopes, but they're still well-known Shiver anomaly, right? So there's still a mirror nuclei difference. I don't know how much it will be affected here, but it will be more, more data will be better, but of course.
Yeah.
It's not guaranteed that access speeds, which will definitely be small. I don't.
Yeah. So
It's not an anomaly there.
yeah, absolutely. So the assumption is not that it completely cancels. It's just that it's small. And if all the models kind of or different calculations agree that it is small, then maybe there's less uncertainty there. With as John said, with large nuclei, that you have the large nuclei are more modified, and so if it's more modified, then yes, maybe the ratio of the nuclear effects cancel out, but you still have just a lot of smearing from the more. I mean, we said that this is approximately A dependent, so you go to bigger and bigger A, you get more modification there. And so this was an attempt with helium 3 and tritium, and so for now I'm just going to show one super ratio. This is the super ratio that the official marathon analysis used. This is the Coulomb-Petty model. This was chosen in part because so you see this nice unity crossing just above 0.3. As we said before, all of the EMC effect ratios measured prior to this had that unity crossing around 0.3. So it is assumed that you're going to have minimal nuclear effects there. And so we're kind of looking for that unity crossing as kind of a, well, that explains things. And that was chosen here. We'll talk about this further in a bit. But that's what was used in the published marathon results, which we're going to now talk about.
Can I ask you a question?
Yes.
That KP curve, but does that tell us, what, like physically, I forgot the super ratio, does this tell us that helium is expected to be slightly more modified than tritium?
Yeah, so this says that helium 3 has different nuclear effects than tritium. It doesn't, it's not necessarily more or less because, let me think about that and qualify that I haven't thought of the more or less. But it's different. That's the key takeaway. It's very similar at low x. It deviates more as you go to higher x, but it's only by 1%. So results. What did we get from this? Helium-3 over tritium ratio. We take our data from the targets, we divide them by each other, and we get this. This is not F2N over F2P. This is just F2 helium-3 over F2 tritium. There's not really, I mean, there is physics here, but there's not the physics that we're talking about here. This is what we got. And then we took that super ratio that I just showed. We input that into the equation for getting F2N over F2P, and we get this. Voila. So we see this slope like we talked about, and then we see this leveling off as we go to higher x. That's interesting. That was not in the Fermi motion only extractions, but if you squint hard enough, you might say this is having an upturn, but it's also within error bars, so maybe not conclusive as far as that, but certainly doesn't look like it's going down further. And so, okay, back to weird nuclei. We have helium-3, we have tritium, we also have deuterium. We can look at their EMC effects, right? So here I'm just going to flash a few plots from my thesis. These were made 2.5, 3 years ago, so yeah, just note that they're old. They're not from a publication, they're from my thesis. And so we say, okay, well, we want to look at these EMC ratios, and we get this. This, of course, not isoscalar corrected. We used the marathon isoscalar correction extracted one slide ago to get that, and we get this. So marathon isoscalar helium-3 to deuterium EMC ratio. But where's the zero crossing? We said nuclei have this crossing at 0.3. Where is that? That's weird nuclei. Put a question mark because we're going to talk further about that. There's a lot to discuss there, just as to what we understand and where we're going with that. So, right, marathon also, I said we have deuterium so that we can do these EMC ratios. We also have proton, hydrogen. And so we can do a D over P ratio as a normalization check and get F2N over F2P. Now, if you recall from those F2N over F2P from D over P plots, like ages ago, those they deviated at high X, but everybody more or less agreed at the low X region. There was no real controversy there. So we can say, okay, well, we took deuterium at all kinematics so that we have that for the EMC ratio, but we only took proton at the low kinematics so that we don't, low X kinematics, so that we don't eat up the beam time that we want to use for better statistics on everything else. We just did it at low X so that we have this kind of normalization check. And we get this, D over P. This is not F2N over P, this is D over P. So marathon is this line with the dashes through it. This is from the marathon publication last year, we'll say. And also plotted were the old Slack D over P data that were used for the previous F2N over F2P extractions. And you see that we have dramatically smaller error bars, and we are in very good agreement with past data. So that's a good sign that we're on the right track. And so F2N over F2P, the extractions ought to agree between our targets if we understand them correctly. Now, we said, okay, everybody more or less agrees at low x. We have this notion that nuclear effects are minimized, cancel around x of 0.3. So we can say, okay, let's do the F2N over F2P extraction from D over P, from helium-3 over tritium. We can also do the same thing for the EMC ratios. So helium-3 over deuterium has a super ratio involved. Tritium over deuterium has a super ratio involved. You can do all of these and say, okay, well, if you extract F2N over F2P from all of those in this region where we don't think there is much nuclear effects, the extractions ought to agree there. And you see here, they don't. In particular, helium-3 over deuterium is really high. I didn't have one where the normalization wasn't already applied to these black tritium over helium-3 points, but that was shifted down to agree with D over P. And we see, okay, well, helium-3 over deuterium also needs shifted down. And when you try to make everything agree in this region where nuclear effects ought to be minimal, you come up with, tritium over helium-3 needs to be shifted down by 2.8%. Tritium over deuteron needs to be shifted down by 0.4%. Helium-3 over deuteron needs to be shifted up by 2.4%. And you add all those up, everything is accounted for, everything agrees nicely, and we said, okay, well, clearly there's something going on that we just got the helium-3 tritium wrong. Maybe it was maybe we didn't have a good handle on our target densities. Maybe the fill was a little bit high, maybe the fill was a little bit low with the gas, and so that is our check that we should do that. And so we apply these normalizations and we get to F2N over F2P as published by Marathon from the helium-3 over tritium ratio, and we get this. Blue dots are Marathon, red dots are JLab bonus, which is a different experiment doing it with D over P, but measuring the recoil proton. They're measuring a recoil in order to constrain your nuclear effects in the extraction of N over P. And then the green hatched line is your previous slag extraction. And we see, hey, that sits right in the middle of more or less everything that we feel like we understand. That's fantastic. And what does that do to that EMC ratio that I was showing before, our helium-3? We shift it up, we apply this new F2N over F2P with the new with the normalization baked in, and lo and behold, this unity crossing pops out that we expected, which that's pretty cool.
Well, isn't that more statistical fluctuations? I mean, it's unity, period. Where would you see a crossing there, given the error bars?
Yeah, so you're absolutely right. We do definitely have statistical fluctuations that kind of throw things off. So yeah, when you look at the strength of the EMC effect here, you might have a big error bar there because we poured over the data for months trying to figure out what's up with these humps, because that and we had 3 different people analyze the data. Everybody got that out. As best we can tell, it's just statistical fluctuations that are a little unfortunate, but that's life. So, right, that then leads to the official Marathon EMC ratios. Previous plots of the EMC ratio were from my thesis. Marathon PRL is currently in preparation. I think there's discussion of like a second round of comments to the collaboration soon. These are the non-isoscalar corrected ratios, so that's what's going on here. We don't have a preliminary isoscalar corrected ratio plot that we're ready to show publicly just yet. And so, but wait, there's more. Okay, going back to your question, super ratios. We only looked at one super ratio there. There's a whole lot of models out there, not just KP. So what can we do with that? We see, okay, well, all of these different super ratios we took from this Afnan paper. I don't remember what year it came out. It was early 2000s. And we plotted those. We added this KP plot or KP line because that wasn't available at the time of that publication. And we see that we've got all of these different options. And KP and this FDIV PST plus CTEC 6 plus 6 quark bag model is the only other one that actually predicts that unity crossing in the super ratio. So that's just interesting to note. We said hyphenated models include exotic effects, so like off-shell, 6 quark bags, those sort of things, charge symmetry breaking. And okay, we said, okay, let's plot this. Let's plot the average super ratio of all of these. The black line is the average super ratio. The gray band is your 1 sigma spread. And we see that KP is maybe on the edge of our confidence interval for 1 sigma. That's not to say that's bad. It's just it does sit a little bit far from other things. So maybe we should see what do we see with other super ratios? What can we learn by assessing all of these models together? And so, really all this is just to say that the result before is model dependent. Let's assess the model dependence of the result. So if we instead take our helium-3 over tritium ratio and just extract F2N over F2P with all these different models, and then also with the average super ratio, we actually get this. Note that I did not include the 2.8% normalization here that was applied before. That is a further step of this analysis that I haven't gotten to yet. We want to assess maybe the model dependence of our normalization uncertainty from the PRL. And so here we see, okay, well, of course, all of these models agree pretty well at the low X, and then you do start to see this deviation as you go to high X. So maybe we need to expand our error bars a little bit there. But we do see that they do all more or less agree to a pretty good trend, which is really nice to see that maybe it's shifted up or down, but we do have results that are going to tell us something. And so right now we're using this and we're carefully assessing model dependence and of the result and the normalization uncertainty and its model dependence of the marathon result by looking at all of these other super ratios that you can choose between, just to be a little bit more conservative with this. So carefully assessing that dependence, normalization uncertainty for marathon, and it gives very different results from D over P when you go to high X. That's one thing to note. Even at this X of 0.3 region, depending on which super ratio you choose, it can give different results. And so there's potential implications also for off-shell deuteron structure and off-shell neutron structure. So you can see that if you look at off-shell models and on-shell models for what F2N over F2P ought to be, there's actually this pretty big shift. And so if there's some off-shellness to the deuteron structure, then that's really gonna dramatically affect how we should assess whether they actually agree or should agree at that x of 0.3. Maybe there's some off-shell effects that are not taken into account, and we need to be careful. Further EMC and SRC data are being recorded on a large group of nuclei. I say very soon, that's because I copy pasted this slide and forgot to change that little blurb. That actually started about a month ago. Just came back from sitting shifts, run coordinator stuff, and it's going great. We're taking EMC data, we're taking short range correlation data, we're looking at all of these things. We got a large group of nuclei that we want to look at, and so we'll talk about that actually in a minute. I have a little blurb on it, but weird nuclei, helium-3, the sequel. So we said, okay, well, we're looking at the normalization, we're looking at the model dependence. If the normalization is not settled, what does that mean for that zero crossing that we were looking for? So we have a couple things to note there. EO3-103, we discussed that before, noted that helium-3 had an anomalously weak EMC effect when you compare it to, say, helium-4, and it defied expectations as well. Maybe not as dramatically as beryllium-9 did, but it was definitively not lining up well with predictions. How's that compared to marathon data? Well, if we look at unnormalized marathon data and the EO3-103 helium-3 to deuteron ratio, they actually sit pretty well right on top of each other. So that's an interesting thing to note as well. Maybe something funky is going on there with helium-3. Maybe we both screwed up in the same way. That's an open question. We want to look at that. Recent publication by Shujia Li, another postdoc here, saw an anomalous SRC result in helium-3 with PP and with PP pairs having a much higher ratio of the SRC pairs than predicted, than other nuclei typically have. And so that points to something strange potentially going on. This result is from an experiment that ran immediately after marathon, same target and everything. So marathon ended, 24 hours later, this experiment was running. Maybe not 24 hours, I've slept since then. I don't remember exactly how long this switchover was, but it was the same target, same target, same beams, same detectors. Yeah. And so current and future experiments, we've said, okay, here's what we know, here's some weird things, where are we going with this? What do we want to know? So XEM2, that's the one that's running right now. High precision EMC measurement of many light nuclei, light being A less than or equal to 12, includes helium-3. And so all of these red dots are targets that we're studying. And so this red band is where you've got approximately isoscalar nuclei. This blue band is isobars, so different N over P ratios with the same A. And we're really aiming to learn a lot there. We want to study the light nuclei, we're also studying other things. So we're also simultaneously mapping the EMC region, that is low x, so x less than 1 in the 0.3 to 0.7 region is EMC, but we also say, okay, x of 1 is quasi-elastic, but then we got this short range correlation region where x goes well above 1 and so that's where you've got two nucleons that are interacting and they both are high momentum, equal and opposite. And we can also test flavor-dependent models with calcium-40 and calcium-48. That is, are protons and neutrons differently modified when you go into a nucleus? That's a big open question. Other things on the horizon, just proposed this year, parity violating DIS. Question is the EMC effect flavor dependent? Standard EMC measurements are sensitive to that, like we said with axiom-2, calcium-40, calcium-48, but they're limited by the feasible precision. So you can see here on the left is the black line is flavor independent prediction, where all the others are different flavor dependent models. If you do a 1 sigma shift, you might get the wrong answer, because your statistics might just give you something funny. But parity violating TIS, more sensitive to this. If you take, again, black line is flavor independent. If you do a 1 sigma shift, you still are saying, well, flavor dependent or flavor independent. So you have more discerning power for looking at these different things. That's one thing on the horizon. There's a lot of things that we can look at to really get at these open questions of what's going on here. There's more stuff. These are the things that came to mind when I was working on this, and certainly that's not the only things, but yeah, that's it. Thank you.
So thank you very much, Tyler. We had tons of questions, but if anybody, especially on Zoom or here, yeah, if there are any Zoom questions, please feel free to just ask.
I have one question, slide 29 or 28. When you do averaging, do you have any weight? If not, how could it end up there? Yeah. When you do averaging, do you assign some weight to the different model?
No, we don't have uncertainties for any of these models, aside from KP, which has extremely small uncertainties. And so we just took the straight average. We took the average and then the RMS spread for the uncertainty.
Okay, thank you.
Yeah. Have you actually, or any other people, look at the data or propose some experiments for the Deuterium production in proton nuclear interaction? I thought in the past there always has been effort to include the Deuterium process, and in particular, I think that's how this pion class model was get somehow dismissed, because it really failed the experimental data on Deuterium production in proton nucleus interaction.
Okay, it's been a while since I thought about that. So many moons ago, I was involved with Sequest.
Yeah.
But let's see. So we got the results out. I know that they did not follow expectations, but I have not kept up with that. Last I was involved with that was when I was in undergrad. So at that point, I did not have the understandings necessary to truly answer that question. And then now I just haven't kept up with it. But I think John has something to say there.
Yeah, I was just going to say the Sequest experiment at Fermilab, they published the results for the comparison of proton and deuteron to get at d bar over u bar. There is also data on, I think, carbon, iron, and something else heavy, so lead. So they have some data for what you're talking about. I think they're actually either just had or will be having a collaboration meeting to sort of finalize and in preparation for releasing results on those ratios for nuclear targets. So those should be out soon-ish, at least from the first sort of third-ish of the running, and then both measurements will have higher statistics results later.
And John, but didn't they publish, was it not D bar over U bar? What was they got a lot of publicity, Sequest, was it just D over U?
It was D bar over U bar.
Okay,
Yeah.
so, but they're gonna publish another one with more targets.
I believe that's what John was saying. I have not kept up with that,
Okay.
to be honest.
Yeah, and the heavier nuclei, you're approximately getting the modification of U bar in a heavy nucleus compared to the deuteron to first order.
Can you look at the difference? Helium-3 and tri-down difference, like Guthrie-Summer rule, F2 neutron minus F2 proton divided by X. That give you a valence and that give you a U bar, D bar difference. Here, of course, you have the nuclear modifications. No wonder you have a data, you can look at just the difference divided by X.
Well, I mean, so we certainly have the data that we could do the difference.
Compared to the NMC data. NMC did this Guthrie-Summer election many years ago.
Okay.
Well, now you have a helium-3 and tri-down. See what the nuclear effects is on the Guthrie-Summer election.
Okay, that's not something that I had considered before. So I think I
But
need
you got the
to-
data, you might as well.
Yeah,
I mean, that's
The data is certainly.
Yeah, you look at the data, I will be very much interested.
Yeah, the data is certainly there, so perhaps that is an avenue that ought to be explored.
Yeah.
We should talk about that.
Stan, please ask your question. Hi, Stan, are you there?
He's muted.
Stan, can you unmute yourself?
I can't, oh, there it is, I can,
Yeah,
Let
we
me
can hear you.
There you go.
having trouble with unmuting. So one thing is that it'd be better if you said that X is the light flow fraction, not the moment fraction, because rigorously it's the using the light flow formalism. And X is K plus over P plus. It's frame independent causal. It's exactly the right definition of what X is. But that's just a minor point. We know from Reggie theory that the proton and the neutron are very simple there. The valence approximation, so it's an up quark and the proton bound to a UD diquark, scalar diquark. And the neutron is a d quark bound to a UD diquark. So that gives you very simple light front wave functions. But people tried that just to see if it agrees with your extraction of the neutron or the proton, just to give a simple thing. Because the reason I say it is it gives a complete Reggie spectroscopy of the nucleon excitations, both in N and L. So I just wanted people to look at that. It's just a simple thing to do.
Stan, can I say something about this? So on your next slide, Tyler, on 30, I think? Yes, yeah, exactly, at 31. So my question, Stan, was the same as yours, which is, and also you showed this on an earlier slide, there's a prediction for the quark diquark configuration for the F2 ratio, which is down at 0.25. So when you guys did all your models, did you not include that quark diquark 0.25 value? Like, why are these guys all the high ones?
I don't recall if there were any that have that built in or not. I will have to revisit that and check. If there is not, then I mean, so if there's not, then we need a super ratio that does include that. So
I can give you the models, I can give you
if you can point me to that, then certainly it's easy to just put that in and click go.
Good. John?
Yeah, I was thinking, so I thought the prediction at 0.25 wasn't a quark diquark model, but maybe there was also a quark diquark that made the same prediction of a simpler model. I know there were some.
That's exactly right. There are more than one that predict that 0.25.
Yeah, I think that table is extremely simplified. I took it from kind of standard marathon talks that throughout the years, and so that those numbers may not have strictly kept up with the times.
But there are some of the predictions that give you something in this range, sort of 0.4 something, are for example the Dyson-Schwinger calculations that do expand in terms of a quark diquark configuration. Though of course there's more to it than just that. So certainly in that sense it supports that type of model. But I don't know if anyone has looked at it, looked at the difference between different approaches with diquarks.
Yeah, so the Dyson-Swinger equation with the quark-quark correlations, I think you're right. That one gave a prediction of like 0.41 as you go to high X. But your table holds up very well because we just posted a preprint with the F2 ratios at X equals 1, and all those numbers still hold up in addition to more numbers. But
that's good to know.
but there are various 0.25, like the ratio going to a quarter models, which always have either quark diquark or some other diquark thing in there. Sorry,
No, you're good. Yeah, I gotta learn.
So, sorry, I guess kind of along those lines, is it impossible, your curve has kind of these bumps that are, statistically, relatively significant. Is it completely impossible that there's some kind of physics there? I know the E6 number experiment, their data was did not have that same kind of thing, but is it completely unimaginable that some physics would introduce some kind of weird resonance bumps or anything like that?
To our knowledge, there isn't anything. Marathon data was at a higher W squared than the E03-103, which so we're firmly out of the resonance region. E03-103 at the very tippy-toppy high X was a little bit in the resonance region, but they also did some very rigorous tests of data at various Q squared to ensure that they had Q squared scaling. And so unless there is something really weird that comes out at higher W squared that I have not heard of, I don't think that there's anything but statistical fluctuations. We spent a long time just playing with tighter and tighter cuts to see if we could clamp that down. Maybe we didn't know our optics as well, maybe our tighter focal plane cuts, all sorts of different things, and nothing got rid of it. So it just, as best we can tell, it just statistics.
I'm sorry to interrupt. I have a meeting at 5, so I'll stop recording.
Very good, thank you.
Thank you, Tyler, for this very nice talk.
Thank you.